Welcome to this short video demo of the latest development in the SNE network emulator portfolio, SNE with 100 gigabit interfaces. We'll conclude this session with a short video demo where I'll hand over to my colleague Giles, but first I wanted to provide some context on where SNE 100 gig will fit. SNE is the first multi-port 100 gigabit network emulator to hit the market. Until now, 100 gig network emulators have been limited to only 2 100 gig ports. SNE 100 gig will offer up to 8 100 gig interfaces in a single chassis, along with the great UI, toolkit and other features SNE has always offered. The rise of 100 gig data center and cloud applications creates a need for higher port density. Only SNE can answer the A recent test case shows how SNE with 100 gig can do this. In this example, a VNF vendor was working in partnership with a large telecoms operator who was moving 5G core network functions to a public data center. With the connections being 100 gig interfaces were needed on the emulator. However, the requirement was to send multiple flows, typically of 10 gig or less at the same time, so 2 ports was insufficient. The vendor was able to test a variety of software applications using typical network impairments such as delay and drop packets. In this way, they could verify the application behavior prior to going into a live network. The result? Faster time to market and lower risk of adverse application performance. I'll now hand over to my colleague Giles who take you through a short demo of how this looks.
This is the dashboard screen of the SNE, showing a graphical representation of the chassis. In this case, it contains 4 dual-port 100 gigabit cards, 1, 2, 3, 4. Each of the 8 ports has a link established at 100 gigabits per second, as indicated by the link LED, and on ports 1 and 2, we can see packets being transmitted and received. So I'm now going to reserve ports 1 and 2 for my exclusive use, and now we're ready to take a look at the map screen. This is my network emulation map, which is designed to illustrate the concept of what the VNF vendor was trying to achieve in the use case just described. They wanted to be able to filter traffic into different flows and impair each flow differently in terms of delay and packet drop. So on this map we have traffic coming in on port 1 and being subjected to an IP address filter. If we take a look at the settings of that filter, you can see that we're filtering on a specific source IP address of 192.168.200.10. Traffic which matches that IP address will go down the pass path, where we will apply 40 milliseconds of constant latency, and then we will drop 1% of packets passing along that path. Packets which don't match the source IP address of 192.168.200.10 will go down the fail path, and is then compared against a different IP address, .201.10, and if it matches that, we'll apply a different delay and drop packet percentage. Otherwise, it will be compared against a third IP address, .202.10, and again, we'll apply a different delay and packet drop percentage. After the traffic has been impaired, we will pass it to output port 2. Traffic then comes back in on port 2, through the SNE, and out on port 1, passing in a reverse direction. So I'll start my map running in a moment, but before I do, I'm going to disable all of my impairments, just so we can see the effect more clearly in Spirent Test Center when I enable the delay and the packet drop. So I'm just going to highlight these impairments and disable them. And now I'm ready to click the play button to start my map running. So we can see the traffic flowing along all 3 paths here, as expected. So let's take a look at Spirent Test Center to see how that's configured. So this is Spirent Test Center, or STC. You can see my port speed is set to 100 gig interface. I'm generating just 10% load in each direction, so that's 10% of 100 gigabits per second, which gives an aggregate port rate of 20 gigabits per second. And the traffic I'm generating is an iMix of different packet sizes to simulate real-world traffic. Now, if we look at the table below, you can see the dropped frame percentage is currently 0, which I would expect because we haven't enabled our drop packet impairments yet. And if we look at the basic counters tab, you can see the short-term average latency is 7 or 8 microseconds. So that's the intrinsic latency with no impairments applied. Now if we go back to the SNE, and I will enable the delay impairments. So that's all 3 of them now enabled. We'll go back to STC and have a look at the effects on the basic counters page. You can see the short-term average latency is 40,000, 50,000 and 60,000 microseconds. Let's just show that in milliseconds to make it a little clearer. So 40, 50 and 60 milliseconds, which matches what I have set on my map. So 40, 50 and 60. So I'll now enable the packet drop impairments as well. That's all 3 of those enabled. So what we should expect to see is 1%, 2% and 3% dropped packets on the different streams. We'll go back to STC, switch to the advanced sequencing tab, and here you can see the dropped frame percent rate of 1%, 2% and 3%.